homework, it's again only 3 questions, but the middle one's a lot longer, although it starts off virtually the same as the last homework set. The first problem, 5 points each, is to determine if they're linear operators. So for each one, you're doing your tests as we talked about last class period. I think it was Indy asked, could I do another? And I said, well, you're going to have some on the homework. So this is a bunch of them. And then we have the big one here, which I have to admit, I did not go through and do my calculations on this yet. So I assume it's going to be easy. By easy, I mean you use your integral table, and if you know your rules, you can do it. And then the last one is actually not very hard. So I'm wanting to work with you on this. I remember to bring my book, and I remember to bring my table of Gaussian integrals because this is a Gaussian function. So I am totally prepared today. So being as I'm helping you, what would you like to focus on? And because I'm helping you, I'm going to have you explain what you're doing. I'll try to write down what you say and help you when you have questions, but I don't want to just do it and you say, oh, yeah, okay, I can copy it. Okay, so what do you want to do?
I guess personally, I have, because I took a look at it a little bit earlier. I guess I have a few more questions on number 2 than I do number 1. So I would say if we could start with number 2.
Okay.
Because I guess I have a few more questions regarding the actual questions than I do with part 1.
Okay, so start off, tell me what your questions are or what you like.
Well, some of them might be just me not thinking clearly, but when, for instance, part A, it says, what is the value of A in terms of the other constants?
Yeah.
Is that to normalize it and then solve for A, or is that to just solve A as it is?
No, the wording here is, I think, pretty standard. And what it means, it doesn't say the word normalized because we want the student to realize this has to be normalized. That's how I find A.
Okay.
And so you obviously were thinking that, just not clear on if that's what the wording implied. It is. It's the way you find A is by normalizing.
Okay.
Or by forcing normalization.
And then what is the probability that the particle's position is in the range? That's just solving for the no, part C is asking for the expectation value for position. So is that just the integral of negative infinity to infinity of the probability dx?
That's the normalization condition, what you just said. That 1 is equal to the integral from minus infinity to infinity of psi mod squared dx. That is, I think, what you just described, isn't it?
Yeah,
and for the expectation value, what's the difference between? Sorry.
The expectation value, the difference is the fact that we're not saying it equal to 1.
It's not just that. There's one other very important difference. This has the operator x.
Oh, yeah. We have, so it'll be the integral of negative infinity to infinity of psi star x psi dx.
Right. So that's the difference.
Okay. Now, is part B asking for us to integrate over from x to x plus dx?
No.
What is B asking?
Because it's from x to x plus dx, your range is only dx. And so what you do when we did this here, we integrated the probability of being in range dx over all possible x's. But here we're only saying in dx. In fact, logically you probably would have done these in opposite order, because you have to first identify that the probability of being in range dx is going to be, well, yeah, I'm not going to put something in front that I'm going to regret later. It's going to be psi mod squared dx.
Oh, okay.
Right, that because you have to.
I guess that was kind of confusing me on what exactly it wanted. But now that,
Right.
because at first I was thinking that we had to integrate the probability, but it's just asking for the probability.
Yeah. The see, I get the terminology tangled up, and so I can say things wrong, and that would give you a wrong impression as well. Psi mod squared is the probability density. It's the probability per unit, if it's linear, distance, if it's area, and so on. So psi mod squared is a probability density, and then to get the probability, I have to multiply it by a range. And if it's dx, it's a small enough range that it's not changing, and so I'm done. But if I'm going from a finite distance, then I have to integrate all of those along the way. Adding up all of the psi mod squared dx's from A to B.
Okay. Well, in that case, I guess that answers most of my questions for A through D.
Mm-hmm.
But then going down, I guess I'm a little confused on E, but for the most part, did we go over the standard deviation for momentum?
Well, it's going to be the same rule.
Or, I mean, okay.
Right, so you remember the standard deviation rule. So if it's x, it would be
Square root of x squared minus x squared.
And so if you're doing it for momentum, and I made this morning and didn't actually sit down and do any calculations. Part of me says, well, because we have the uncertainty relation, how am I going to be able to find both of these at the same time? But part of me says, well, the operator is just going to give us simple functions that we can have the momentum value times the same size we started with. So it should work. So I haven't done it, but I'm pretty sure that everything is copacetic.
Okay. Okay, I guess that answers my questions for part 2. So I guess for myself personally, I can do those calculations.
Mm-hmm.
So I think it would be more beneficial to focus on understanding the problems.
Okay.
If that makes sense. So I was wondering for now, rather than doing the calculations,
Mm-hmm.
for those, could we talk about part 3?
Okay, for part 3?
Yeah.
Okay.
Go ahead.
Part 3 is essentially a math problem. It's these forms here, e to the ikx, that is describing a wave that goes on forever. So it's just it's a wave, but the way we think about these is a left going wave and a right going wave. And so the flux is talking about the net amount of wave passing with the left and the right. Right? Those are things we haven't learned yet. So that's why I put what the flux is, so that it just becomes a mathematical problem. Then when we actually get to this, we can say, we've already looked at how to do this calculation. So it's basically throwing in a math calculation that later on we're going to apply in the quantum.
Okay.
So in terms of understanding the problem at this point, just think of it as, okay, it's a math problem. How do I do the math? So you're just doing psi star and psi, making sure that you're good with doing the complex conjugates and going through the math.
Okay. So then, for that problem, we're just solving for J.
Yes, you're just solving for J.
Okay. And we just plug in the values that we get from the wave function into that.
You're going to plug this wave function in. Yeah.
And then just and then plug in the term. Okay, that makes much more sense because I was thinking of something.
Yeah. It's not something you're supposed to already know.
Okay. Okay, so that answers my questions for the part 2, part 3. So I guess working through part 1 would be beneficial both for myself and then also for Indy.
Mm-hmm.
So I think maybe if we work through the problems at part 1 until we're good on, or until we're out of time, I guess.
Okay.
So,
1A. Okay. I've actually got it printed out. I don't need to scroll around. So what are the 2 conditions that a linear operator must obey?
The first one is that, are we using O1 or O?
Well, yeah. Does our textbook use L? I actually had this problem, and I wrote half of it in O and half of it in L, and then I changed them all to O. Because I think, what does the textbook use? We can use L if you like L, or we can use anything else if you want.
Either way, it's fine. But f of x plus g of x in the brackets equals O of fx plus O of gx for the first one. And then the second one is, I forget if it's A is on the outside or inside on the left side.
Well, it's on the inside one and on the outside the other. So.
Okay, so A of fx, and then that equals OA or AO of fx.
Okay, so let's just do those tests on the first one.
For this, are we saying that psi of x is our function?
Yes. So yeah, psi of x. Over here I had f and g, but in any case, it's the wave function. Yes.
Okay. So we have. I understood this morning, so let me see if I can take a moment to wrap my thoughts. One quick question since we're using psi of x, when we say g of x, does it matter what we use for that?
No, the psi is your wave function. So basically what we're saying here is for number 1, we're going to let psi of x is equal to f of x plus g of x. And for test 2, go ahead. There's a delay, so we end up talking on each other. At least on my end, it sounds like.
Oh, okay.
Well, on that one, it's actually, yeah. Those are the substitutions we'll use.
Okay, but then when we go, to the other side, to break that apart,
Yeah.
do we just use psi again?
Well, doing our test on this side here, this here applies to there, right? And then we're going to replace, and it's just going to be f of x and g of x on the right-hand sides. Yeah, I should have had the a there.
I mean, because in the first case it'd be x cubed times your
Well,
psi of x.
let me back up and explain in a way that I think will be clear. The psi is going to be whatever O is acting on. So if you look at condition 1, on the left-hand side, we're going to have this is psi.
Mm-hmm.
On the right-hand side, we're going to have this is psi 1 and this is psi 2, just to keep them straight. But they're still psi from that relationship. So when we apply the rule, I'll go ahead and do the first one just to make sure we're real clear on it today. I'm going to take the left-hand side and say operator 1 acting on this psi is going to be, and I want to change back to green, x cubed times this entire psi of f of x plus g of x. So I did not change what was in the bracket.
But in essence, it's psi of x.
Yes. And so it was psi of x before and psi of x after. And then we have x cubed out front as the eigenvalue.
Yeah. So, and then that would equal x cubed times psi 1 plus x cubed psi 2. Or x cubed f of x plus x cubed g of x.
Right, because psi 1 was f of x, psi 2 was g of x. That's why I just...
Okay, that makes more sense because that passes.
Okay, so that passes.
So then, for the second one, we have a of psi x. Or I mean,
Psi is AFX. For the left-hand side, psi is AFX.
So then we have x cubed a psi of x, or whatever, f of x. And then that would equal...
Notice I put it equal with a question mark because we're testing.
Yeah, or testing that it equals a times x cubed f of x.
Does it? If a is a constant? So that means that a passed both tests, it's linear.
When we talk about things like derivatives and integrals, do we include that as part of um, the function? Or
It's the integral derivative is going to act on the object. So when I do this, the d dx of psi, my answer is going to be whatever that derivative is. Since I don't have a specific function for psi, it has to work for any psi. I leave it showing the derivative.
okay. So in this case, we have x. For the first one on the left side, we have x d over dx times our f of x plus g of x. And then on the right side, we have our x d over d of x times f of x plus x times d over dx g of x. In which case it passes.
Right, it's going to pass again. I'm starting to wonder if I made any of these fail, but we saw from class last period that there are plenty that can fail.
Out of curiosity, with these, can we apply these tests to just anything? I mean, does it have to be a specific example or a specific use, or
Well,
just...
You could find something that is not a linear function. You could find a psi that it works for. For instance, if you say psi is equal to a constant, it probably is going to pass whether it's a linear or not. So it has to pass for all functions, not just for one example function.
Okay.
Now, if it fails for an example function, it fails. But you would have to test every possible function for passing. So you can disprove, just like with science, right? You can disprove with a single case. It would take every possible case to prove it, which is not possible, except for doing it in general.
Okay. For the second one, we'll have x times d over dx a f of x. And then that will equal our a times the quantity x d over dx psi squared, or I mean psi of x, or f of x, sorry. In which case, that would pass. Yes, that would pass.
Now, you're answering these, and you're correct that they pass. It is kind of important that at least in your head you can say, like from one, well, the derivative of the function, I have function A plus function B. The derivative of that is derivative of function A plus derivative of function B. So it's important that you're thinking those through. I haven't stopped you on any of them because they are pretty obvious.
Yeah. In which case, I mean, for instance, if number one was actually, never mind. I was gonna say if it was this case, then it would be different. But even in that case, it's still the same. So that just ignore my thoughts.
Okay.
So we have next one.
And now we head off into stranger territory.
are we treating lambda as a constant?
Um, lambda is, yes.
Okay. So for our first test, we'll have for the first one, since we're dealing with the conjugate,
Mm-hmm.
would we still put the conjugate on the other side? Or do we have to change that to fit?
You're going to put the conjugate here.
Okay, that makes sense. In which case it's lambda f of x g of x star d of x. On the other side, we'll have lambda times your fx star plus your lambda g of x.
Okay, is that pass or fail?
I guess I'm a little unsure on this one because I'm not sure if for the wave function is it always of the form where I is in the exponent?
No, it does not have to be.
Because in that case, wouldn't it not pass if you have the conjugate of the two in the parentheses versus the conjugate of each separate part? Or they
Remember, the star just means you're replacing all of the i's with minus i's, right? So that's always going to be just replace all the i's in A with a minus I and replace all the i's in B with a minus I.
okay. In which case, then yes, it would pass. For number 2, we have lambda times a side x equal to a. Now for this one, for part 2,
Yeah.
can A be imaginary?
Yeah. I was just looking at my book to see if there was any mention of that. The actual when we talk about the Hermitian operators is when we have this stuff in the book, and it says I didn't find anything there for if it has to be imaginary or not, but I'm pretty sure it can be imaginary, and that makes a difference to our answer.
In which case, since it can be imaginary, I want to say it does not pass.
Okay, because you would have
Because your A would be on the inside, that'd be the. In which case you'd have
I forgot the lambda.
the lambda.
And there we have a difference because A versus A star.
Yeah. Which those aren't equal. So it fails. So for part D, since we have our psi of x is in the as the exponent, do we have to first bring that down,
Nope,
or does it matter if it's an exponent?
nope, we're good with it like it is.
So for this one, for part one, my gut wants to say e of psi x times in parentheses f of x plus g of x, but that doesn't seem right. So,
It should be like this.
okay, so we replace it as the
Right, every time we're replacing psi with f of x plus g of x for the first half here of test one.
I guess having a difference in the way we did it is just something that's different. In which case we'd have e f of x plus e of g of x. In which case yes, those should be.
If we take the left-hand side, what's the rule of having exponential to a plus b? You can separate into two separate exponentials, but how do you do that?
Oh, no, they're not equal. Because in order to add, you have to multiply.
Yeah.
So that fails. In which case, we don't have to do the second test to show that.
Right, we don't have to do the second one. Since we're doing it in class, let's go ahead and do it anyway. You don't have to do this for your homework, right? Because if it fails, it fails. But doing the second half, it'll fail this one too. That's why I want to do it.
Okay. So for here, we have e to the a psi x, or psi, f of x, sorry. And that would, testing if that equals a times e of f of x. In which case it doesn't.
Yeah, it clearly fails. Oops.
So for the first one, we have d of dx, and we're taking the derivative of f of x plus g of x. And then our plus a, testing if it's equal to our d of f of x with respect to x plus a plus our g, or d over dx, g of x plus a. In which case, no, it's not equal.
Fails because you have 2A on one side and A on the other side. So fortunately, we don't have to go to part B where we'd have two different A's. We have to change one of them to a different letter.
Yeah. And then for number 2, would just be R.
Let's just use C instead of A for the test.
Okay. C of x plus A times, C times. Which is, yes, it should be equal because you know that constant. Right. Already confusing myself. They're not equal. I meant to say.
You're correct. They fail because on the left side, the A is by itself, and the right side, the A is multiplied by C.
I confused myself and I wrote C twice. So then I had to go back.
And the last one.
Last one.
Whoops. Put two D's.
The first one's x. Fx plus which party?
Yep.
Now,
By the way, you notice that it has x primes in the integral, so you don't have the variable of integration and the limit both being x.
yeah. So for the when we're testing against these two rules, I don't think it would make a difference, but would it make a difference having, say, a definite interval versus an indefinite interval?
You wouldn't have a function of x anymore after doing it, but for our purposes, I don't think it'd make a difference. You would just have a constant. This operator always gives a constant with, no function following. This is clearly it's not going to work for our quantum physics where you have to get back the original function. In fact, most of these don't work for our quantum physics where you have to get back the original function.
Yeah. Makes sense.
All right, that's all of them.
I guess since we do have still a little bit of time, if we could work on either F or I, because we haven't used a um, expectation value other than just x and x squared.
Okay. Let's go ahead and let's do the kinetic energy one, I. Just randomly choosing, unless you have preference to say, no, I wanted to do.
Okay. No, I was just wondering to have experience with a algorithm that doesn't have just x or x squared.
So what is the kinetic energy operator?
Off the top of my head, I know this is probably wrong, but I want to say it's negative h bar over 2n times the partial derivative with respect to x.
Okay. You missed all the squares, but otherwise you were right.
Squares.
It's h bar squared, and it's the second derivative.
Okay.
And now, partial, if you're one dimensional, it doesn't have to be partial. Like in 1E and 1B, it wasn't partial because they were one dimensional, right? If it's multi-dimensional, like if you had x and y, or if you have x and t, well, then there's a world of difference between the two. But if you only have one variable, it doesn't matter.
Okay.
Okay, so
In this we have that the expectation value is equal to the interval negative infinity to infinity AE to B
now
negative.
we better put a star.
That's right. I forget that there's a difference.
Now, it does say a is a real constant. So you know what? It said a is a real constant. You can leave it a. A star is technically correct, but since it says a is a real constant, you can be.
I guess I'll leave it as star just because that will.
Yeah, so you don't get confused if you look back at it.
In this case, we don't have any i's, so we don't have to change that.
Right?
And then we have our operator, which is h bar 2n, which is times psi, which is and then the units.
I tried to use colors to separate things a little bit. So you have the operators in red, the psi is in purple, psi stars in black, and dx is in black for whatever reason. Okay, now what?
Now, one quick question. Since negative h bar squared over 2m is part of our operator, but since that's a constant, can we still pull that off?
Sure.
That out. Just because I guess that's something I've been used to doing, so. And then we're going to find the second derivative of e to the negative ax.
Right.
First derivative is negative a 2 ax squared. So
Okay. Did you get the same thing for the first derivative? Because you were speaking, but I couldn't make out what you're saying.
oh, sorry. Yeah, I got negative 2a times e to the negative ax squared.
It's minus 2ax. You're bringing down the derivative of the
Oh,
exponent.
yeah, that's right. Sorry. And then,
Oh, life was so easy if you didn't have to bring down the x.
yeah, it definitely would have made life easy. And then for the second derivative, it's equal to 4a squared times x squared.
Got to use the product rule, right?
Yeah,
So you have
never mind.
minus 2a e to the minus ax squared, then minus 2ax times minus 2ax. I always want to shorten things up and factor stuff out on the way. But if you factor it out on the way and you didn't see the method, it can get frustrating.
Yeah.
So here it's as explicit as can be. I didn't even factor out the minus 2a.
Yeah. Right.
Oh, brother. So there I put red for the first function and left purple for the second function. So you can see the product rule in action.
Yeah. Yeah. For I just switched, and so you have that the 4a. Does it matter if we factor out?
Well, you know, I'm going to, yes. It doesn't matter, no.
So if for mine, I didn't factor out the 2a e to the negative a x squared, so I just left it as it together.
Okay, so now we can put that into our integral. And I see we're 5 minutes over now, but I don't know. Nobody uses this classroom afterward, so if no one uses yours, we can go. if somebody uses it, we better stop.
I guess I can see real quick if there's anyone out there. I don't think there is, but especially on a Friday afternoon.
Yeah, Friday afternoon. It's a ghost town afternoon.
I know there's, as far as I can tell, there's no class after this.
All right, so we can finish up.
In which case, oh, okay.
Those are the two separate integrals that you should have. I took out 2a, so you would have 4a squared, a squared, and 2a.
I see what you did. I was confused why you had gotten rid of the 2a and then in the x squared, but now I realize, yeah.
Let me do some color coordination to help us a little. That, and then, whoops, that was bad. So that's what my colors are going with.
Yeah. Now in this case, well, the first integral is symmetric. Right?
They're both symmetric.
Well, yeah, they're both symmetric, but on the first one, we have x squared, which I don't. Did you say you had the table? Otherwise,
Yes, I have it right here. Here, can't you read it? So
luckily, it didn't kick me out of B class.
So this is going to be 2a times, and then our form is going to be 2 times because it's minus infinity to plus infinity and it's symmetric.
Yep.
And go ahead. I'll write over here the thing while you're talking.
Okay. So since we're taking e to negative 2ax squared, are we splitting that apart, or are we just leaving it as, oh, okay. You just substitute a new value.
So that's the integral form for the Gaussian integral. And I put in b's here so we don't get a and b confused.
And then the other one,
In which case, this would, for the first one, it would reduce down to 1/2, so 1/2 times 5.28 square. Right.
You have the 1/2, but you have going from minus infinity to infinity, so you double it.
Yeah, and then, yeah. Does it matter that I just simplified that top one down, whereas you left it out? Does that make?
You mean you went ahead and canceled 4A with 4 and A?
Yep.
No, it's fine. Huh. No video has been detected. The system will shut down when the timer expires. Not sure why, but that's okay because we're done, right? Now you just
Yeah,
put it in.
and then you just plug it in.
Okay.